Okay, so where we left off last time, and I know I keep drawing this picture, but this is sort of the picture that we're going to live with for a heck of a long time. This is our space-time manifold with coordinates, and we know that at each point we have this full-on architecture of vector spaces, covector spaces, tensor product spaces at every point in space-time. I like to draw it this way, but it is sort of this fiber bundle. And what I talked about in the end of the last lecture was the metric tensor, g mu nu, which of course is a function of space-time. Oops, I can actually write it this way: dx mu dx nu. This metric tensor is a function of space-time. It's the thing that we pick out that, in some sense, well, it establishes an inner product at every single point because it is a metric tensor that exists at each point in space-time. And a metric tensor, by the very definition that we use for it, is what mimics these inner products. So this is what allows us to actually compare vectors in V with each other through the inner product, and it also allows us to establish this one-to-one correspondence between V and the dual space. In fact, that one-to-one correspondence between V and the dual space is what this metric tensor actually is, right? It is a map that it's a map that takes vectors and gives vectors. So g mu nu is looking for two vectors, right, and will ultimately give you a real number. So if you put in one vector, g mu nu, and you just put in one vector, it's now waiting for a vector to give you a real number. And the thing that waits for a vector to give you a real number is always an element of the dual space. You can review that from our earlier lectures if you've forgotten about that. But the point is we've established, by picking this metric, we always knew that picking a metric tensor was an important step in a vector product, in a vector space's little definition and existence. But picking a whole darn field does this at every vector space for the entire space-time. So you might think for a second that, well, that binds all these things together somehow. Somehow this field binds everything together in a way where we might be able to compare things here with things here. And the answer is yes and no. It and alone, all by itself, as it's sitting here, it doesn't very easily allow you to do that. Ultimately, it does. But we have to go through a mathematical process where we have to define a way to break the seal in principle between all of these things. So we're going to learn a technique that actually breaks the seal between this vector space and all of its adjacent vector spaces. And by adjacent, I mean essentially all of the vector spaces on the manifold. The seal will be broken, and we'll be able to compare vectors from this vector space to that vector space, or to any vector space that exists on the manifold. And that breaking of the seal, I keep saying, oh, there's, you can't compare vectors from this space with that space. They're totally independent spaces. They're mathematically, it's mathematical nonsense to add them, subtract them, compare them in any way. And I keep saying that, so when we come to this moment where we actually break the seal, you see what an important and significant mathematical step we're taking. We're actually breaking this sort of impenetrable wall between mathematical objects that, and we've got to come up with a way to do it, otherwise we'll never be able to move around in space-time. And that's essentially what we're going to do now. And the mathematical construction that allows us to ultimately go between these vector spaces is called the connection. And it's a very, very rich idea that starts here in general relativity, but also exists in quantum field theory in a major, major way, in a slightly different form. And someday we'll get to it. But the principle of learning how the connection works is critical to understanding both of these tremendously fantastic, magnificent pieces of contemporary science, right? It's a very important mathematical idea. So that's the purpose. This lecture is going to be devoted to the connection. All right, so to do our first approach to the connection, we're going to use the elementary example, sort of the elementary method. The elementary method is called elementary because we're going to lean on our picture of vectors a little bit, which I usually don't like to do. The little pointy thing version of what a vector is. But it really does do a good job, I think, of getting to the core of what a connection is all about. And then maybe we can use the more abstract method second. So considering a point P, which is located at position x in a space-time. And then we're going to consider a nearby point Q, which is located at position x plus delta x. Now when I write x, I mean x is actually 3 coordinates, right? Or 4 coordinates, because this is space-time. So when I say x, I'm talking about x0, x1, x2, and x3. And when I talk about x plus delta x, I'm talking about x0 plus delta x0, x1 plus delta x1, etc. Right? So that's what these 2 different points, that's what they're located at. And we write this, this is always shorthand, right? Shorthand for this full construction when we do this. Now we also are going to assume the existence of a vector field, right? And that vector field, I'm just going to write down the components of that vector field as x alpha of, well, say some field coordinates, say x, y, I guess z, right? So z is a point in space-time. X alpha, these are the components of a vector field located at a point with coordinates z, right? So the components of a vector field at the point of a coordinate z. Therefore, the components that this vector field puts at the point P is going to be x alpha of little x. And the components that this vector field puts at the point Q is going to be x alpha little x plus delta x. And so those 2 vectors already exist because we have a vector field stipulated to go on top of the manifold. And where's the manifold? Well, the manifold is all of this stuff, right? I don't have the coordinate lines drawn, but presumably there are coordinates of some sort all over this manifold. Four of them, right? Just these guys. So the vectors themselves live in some other mathematical space that is attached to this point, and we could place these components inside that mathematical space that's attached to this place. And it would be a little arrow, or it would be, you would be able to plot it in R4, or, in 4 dimensions. If there were 3 of them, you'd be able to take these components and plot them like a little arrow. So for the sake of squeezing all of this into one place, let's draw that arrow right here, understanding that it really exists in this other space called the tangent space, which we've decided was going to be the tangent space at the point P, right? That's the space this arrow is really living in. But we're going to draw it right there because it helps us to understand what we're going to do next, which is we know that there's also one of these guys at Q, right? There's a guy at Q. It's some other vector in some other tangent space. In fact, it's in the tangent space TQ. But we've done exactly the same thing. We've taken the components that are calculated because of the existence of the vector field. We've put in the point that it's at Q, and that's exact. Q is exactly x plus delta x in the coordinate system. And we understand that there is a vector inside the space Q. Let me make my Q like that. And that is also established to exist by the virtue of the fact that you have a vector field stipulated to exist. So now we want to talk about this idea of taking this vector here and moving it, leaving this space, literally leaving this vector space and moving it to this vector space, which is very close by, right? This distance is delta x, right? That's what this is. That's delta x. And we're going to move, let me make that a little straighter while I'm at it. like that. That is delta x, right? And that's a small distance, we're going to say. And you know what, I don't think I want those little points because I'm going to have a lot of messy stuff here soon. So we want to consider moving this vector, leaving that vector space and bringing it into this vector space. And we want to do this in a way that is parallel, right? We want the resulting vector here to be parallel to the vector there. And what does parallel mean? Well, you know, parallel means that the vector in this space associated with this space doesn't change. There's no derivative, right? There's no the change in this vector between here and here when I move it is zero. There's no change, and that would be consistent with our idea in, say, regular flat space. If I had, you know, in the space of classical physics, if I took the vector here and I did a parallel transport to a vector here, it doesn't change. It's pointing in the same direction here as it was here. Well, I want the same thing to happen here. I want the vector p, when I move it out of this vector space and into this vector space, I want it to be pointing in the same direction. The problem is we have absolutely no way to naturally say that it's pointing in the same direction. Ultimately, that's the problem. We can't assert that there is a vector here that is parallel to any vector here. There's nothing we have that allows us to say this is the parallel vector in this space to that, and this one is not, right? In other words, the idea is if I take this vector and I shift it over here to the so-called parallel vector, right, which I might even draw as, let's say I wanted to write it down as x, a, x, parallel, right? I'll do that. I'll give it a special name even, parallel. And I want to be able to say that the vector field puts a vector at q in the q's vector space, in the q's tangent space here, but that's not the one that's parallel to this. That's just the vector that x put in here. It's not like it's not like the vector field puts a vector in every place that's parallel to each other, right? Then that would mean that every vector field would only look kind of like this in regular sort of Euclidean space or in the regular Newtonian physics. All vectors would always be parallel for every vector field. But certainly that's not true, right? You have some vectors that look like this, and then they look like this, and then they look like this, and then there's all these streamlines and fields and solving all of those first order differential equations you remember solving where you end up with streamlines, and clearly those vector fields don't all point in the same direction. So there is this issue here with the curve space when we've isolated all of these vector spaces from each other. You can't figure out what is parallel to what. All right. So now that we know that you cannot do this, we're going to assume you can. Assume you can figure out what is a parallel vector. And what would that give you? What power would you have if you were able to figure this out? And the first thing that comes to mind is you could think about how does this vector, the vector field, the vector that the vector field puts at Q, how does that compare ultimately with the vector that the vector field put at P? And the way you can compare them is you can compare this vector with this parallel vector, and you could say, for example, oh, if x alpha x plus delta x, if this vector here was equal to that vector, you could say that this vector field has no derivative in this direction. It doesn't change in the direction of delta x, right? Because when you started at x and you had a vector and you went to delta x away and you got this parallel vector, well, the parallel, by the very nature of what it means to be parallel, is that the vector field didn't change. You're in this circumstance, right? You're in this circumstance right here. Likewise, if it does change at this point, remember, this vector is inside the tangent space at Q. Both of these vectors are in the tangent space at Q. So now you can compare them. So if the vector field gives you a vector that's different from this parallel vector, now you can look at the all-important difference between the two, right? You can look at the difference between these two vectors. And that would be able to tell you something about the derivative. You could take, say, the difference between these two vectors and perhaps divide by the difference between the 2 points, the coordinate difference between the 2 points, take the limit as this guy goes to 0, as q gets closer and closer to p, and that limit, the limit of the size of this, well, that's the difference, that's the dependent variable here, or the independent variable here, so you would end up with a sensible thing you could call the derivative of the vector field. So that's kind of interesting. So that's actually what we want to do. We want to be able to define the derivative of a vector field. That's our goal. And it's really important to have a derivative of a vector field because all of physics is defined in terms of differential equations. So if you have objects that are modeled as vector fields, or likewise covector fields or tensor fields, we need to be able to take their derivatives on the manifold. And the one important thing that could help us do this is if we understood this notion of parallelism, because the idea of parallelism on the manifold now allows us to compare vectors at 2 different points. What I'm really comparing is not the vector at 2 different points, by the way. I'm comparing the vector at q. Everything I'm comparing ultimately is at q, but I'm comparing the vector field's value at q with the vector at q that is parallel to the vector at p. And so figuring out this parallelism would really help me understand a derivative. So to begin to figure this out, we are going to start by let's actually put the hard question aside for a moment. Let's just say we know what this parallelism is. It's not a cop-out because we are ultimately going to have to deal with it. But let's deal with a few other things first. Let's have a close look at this guy. What this is of course, this is the vector that the vector field places at this location near x. So here's location x, just to make it clear that this point is located at x, and this point here is located at x plus little delta x, right, where, again, all of these are in play. So now, how can we rewrite this to be something a little more useful? And whenever we do this, we always have the Taylor series to work with. And understand what we're talking about in the sense of what these things are. Remember, these are components right now. So this is a function. This is like a real valued function. Well, it has 4 different parts to it, but each of these is a real number. And this is an actual function. And this field produces 2 values at 2 different places, and it's a continuous, smooth function on the manifold, presumably. So we should be able to Taylor expand this without any trouble. And the Taylor expansion of that is going to be very straightforward. It's going to be I'll make sure I make my little x's. The field is big X, and the coordinate is little x. So the value of the field at this nearby point is the value of the field at the original point, right, plus this delta x, this little increment, but it's indexed. We're going to have to index it because we're going to take the partial derivative with respect to the coordinate b in order to make this work, right? And that's a very straightforward application of Taylor expansion, right? Because this term here is dx. Shouldn't be a, it should be alpha, right? Let me make that clear. This should be a little alpha. Dx alpha by d little x b, right? And then it's essentially delta small increment of x b, right? So when you expand this, you're going to get 0, 0 plus 1, 1 plus 2, 2 plus 3, 3. And that's going to be, so the alpha component will be shuffled around and moved in each direction and exactly according to its rate of change, and the amount that it moves, it's going to change this initial value. And this, of course, is limited to the linear term in the Taylor series, right? There could be additional terms, but we will ignore those because we're going to be so close that any term that looks like delta x quantity squared, that is going to be essentially 0. That's how close we're going to be when we get in there. So, this is our Taylor expansion. This is our Taylor expansion of this thing. Now what we'll do is we'll whip up a quick symbol for this term here, right? The term that distinguishes it becomes the difference between the value of the components at the new point Q compared to the values of the components at the point P, right? This difference term here, we're going to give a new notation for, and we're going to call that delta capital X alpha. And this is all very traditional stuff in elementary books on the subject, so I'm not just making stuff up here or adding superfluous terms. You will see this very derivation in a lot of different textbooks. That's why it's the first one that I'm going to do in this process. So now it should be obvious now that the change in the components is going to be equal to x alpha at the point Q, whose coordinates are x plus delta x, minus x alpha at the point x. So that's the change in the coordinates for delta x. So this tells us now we understand how to write down this guy here in terms of our original vector, right? The original vector plus this. And this is all established because we can calculate this, right? We know this function, right? We know what x alpha of x is because presumably we were given a vector field. So because of that, we can take all of these derivatives without any trouble. And so this is a perfectly calculable, completely known quantity because we know how much we're shifting. We can calculate this derivative. We know the value at the original field. Therefore, we have a Taylor linear estimate of the value of the field at Q. And as long as we start thinking about taking the limit as this goes to 0, we'll know the value of this, the components, the value of the components of this vector in TQ. So that's good. So what else do we want? Well, now we've gotten this thing down. The only other thing that we're interested in is this guy right here. Now, in this case, we really don't know anything about this vector yet, right? All I've said is there's some vector here in Q that we can call parallel, right? And I'll put that in quotes because we don't really know what that means even, but we can call it parallel. We don't know its function or its how to identify it. We don't have anything like this where we can take derivatives and make a Taylor series out of it. So we're at a severe disadvantage. But what we can do is we can write down, I'll do it in green, we can write down sort of the similar concept as we did in this case. We can create something that looks, we'll call it this, with a bar over it. I'll use that bar notation. And what we're saying now is that this is going to equal whatever this parallel vector is, right, minus the original vector. So I might write it this way, x alpha at x parallel, right? Now because I wrote parallel, I'm referring to a vector at Q, in the tangent space at Q, right? This thing here has got to be an element. This thing has got to be an element of the tangent space at Q because it's that mysterious parallel vector. And so the reason the notation is selected is this is the vector that we're seeking the parallel of at Q. I guess there should be a Q somewhere in this notation, but we're not going to use this term very long, so I'm not going to worry about it. But that minus the original vector's components, right, at x. So the point is that in the space at P, these are the components. We're going to move that by parallel translation somehow, which we don't know how. We're going to move from here to here, and we're going to come up with this vector as the parallel vector over here. Now this vector will have, these are the components in Q of the parallel vector. These are the components in X. These are two real numbers. In principle, you can subtract them. You can subtract real numbers, right? So the difference in the component values in Q from the component values of P, the difference, the components here versus the components here, that difference we're going to call this number here. And this number is delta bar XA. And once we've done that, once we've decided what that difference is, which is symbolic, totally symbolic, right? This is, all we're doing is cramming what we don't know into something small. And the ultimate statement of that is that I'm going to write x alpha x, this parallel vector, equals the components of that parallel vector equal the components of the original vector plus this weird thing delta x alpha. So now all the mystery is kind of wrapped up in that thing right there. And so if we were to write down everything on our chart, I would write down that this vector here, why don't I'm going to make my point more narrow. This vector here is x alpha at x plus delta x alpha, where delta x alpha is defined here. And this other guy is x alpha at x plus delta bar x alpha, where delta bar is containing all that mystery about how to figure out what is parallel. What is parallel? And then we have, once we have that, we have the ability to find out what this thing is, the difference between the two, because we can subtract this from this, right? And usually that is the order. We take this guy, the vector field x at q, and we subtract from it this mysterious parallel vector, and ultimately we get, for that value, it's going to be delta x alpha minus delta bar x alpha. And that thing there, this thing here, that thing there, this thing here, that is the difference between the parallel vector and the q vector. And that difference related to and divided by this difference between P and Q, that gives us a derivative, because now we're studying some notion of the rate of change of this vector field. The vector field goes from here, goes from this vector here, these components here, to these components here as you move across delta x. That difference in components is measured by this thing. And this thing has wrapped up in it this mystery of the parallel vector, right? The thing we haven't figured out yet, the thing we still don't know, is the notion of if this went from here and ended up here, then we would want the derivative to be 0 because it's not changing. It's the same vector. It's parallel. It's not the same vector because it's obviously in a different space. But it's a parallel vector from this space to that space. And that notion of parallelism is what breaks the seal between the entire tangent space at P with the tangent space at Q. That notion of parallelism is somehow this space knowing, or us knowing, how these vectors relate to those vectors. And we just, we haven't studied anything that can give us a hint about that. But boy, we do now understand exactly how good it would be, because this difference here, right? This difference here would be a remarkable break in the case, because we would be able to formulate some notion of a derivative. So we might as well at this point get technical about it, since we're wishing for things, right? Let me boost the size of the pen and erase some stuff here. Right. Erase these for a second. And now what we're going to do is we're going to actually write down this derivative term. We're going to write this down. And the way this is going to look is like this. We're after the difference between the vector and the vector field. So that would be, we're after x alpha at x plus delta x minus this parallel vector, right? And this parallel vector we've written down as x alpha at x plus delta bar x alpha, right? And now we know how to substitute for that using the Taylor series, which will be x alpha at x plus delta x alpha, where we remember delta x alpha was this term that went delta xb db x alpha, like that, right? And so that minus x alpha x minus delta x alpha ends up equaling delta x alpha minus delta bar x alpha. Now, this difference that we talked about here, this is the difference between this vector here and that vector here, which obviously I just solved again to be that. But we want to take that and we want to divide by this guy, right? Well, that guy is really a little vector interval, right? This is there's components to this, just like there's components to x. There's 4 components to that. So that division is going to look like this, delta x, say c, with a little c there. And so ultimately we have delta x alpha minus delta bar x alpha divided by delta xc. And then of course we take the limit as delta xc goes to 0, right? And this limit here, that guy, is what we're going to end up calling the covariant derivative of the vector field x. But then what does this thing end up being? Well, we can split this up and we can ultimately get the limit as delta xc goes to 0 of delta x alpha delta xc minus delta bar x alpha over delta xc, like that. But this thing is not too hard to see. This thing is simply the partial c x alpha, which is the normal partial derivative of c with respect to the coordinates x Charlie, right? So we end up writing it with that notation, minus this guy, right? Where again, all of the mystery is sort of wrapped up in this term up here, right? So there's some derivative going on here that we're going to have to struggle with. So let's talk about this guy. So as I said, all the mystery is up in this thing here. This, remember, is this is what contains the notion of parallelism, because it tells you how the components of the parallel vector are different from the components of the vector at the original point P. So if you remember the construction, right, where there was Q and here was P and this was delta XC, we're calling it now, because we added we're taking it out of its pure vector form and actually giving it an index. So we want to know, well, how do we expect this thing to behave? We know that if Q gets closer and closer to P, this thing should get smaller and smaller. And in fact, you might think that if this was 0, this should be 0 too. So we might say, whatever this thing is, it should be linear in P, at least when it's close, when it's nearby and small. It should be linear, and not in P, but in this distance between P and Q. So whatever it is, let's give it one linear factor of delta XC, the displacement. And then it's also not too crazy to think that if this is the components of the vector field at P, right, you might imagine that it's also linear in the size of those components. We want it to be linear in this size as well, right? The smaller that is, the smaller this term here should be. This term here should shrink as that term gets smaller. If this was 0, we would expect this to be 0 also. So let's also give it a linear term in the original vector. So we'll give it a linear term there. We'll call it C. We'll call that D. So now it's linear in the vector field term. And actually, I should put that, I should make this just to be completely clear, because you got to know where these things are, right? X, D, at little x, right? So it's got to be linear in those two things. But remember, these are this is 4 components and 4 components. So it's got to be linear in every combination of those components, right? It's got to be linear in x0, located at x, delta x0. It's got to be linear in x1 of x, delta x0. It's got to be linear in x2 of x, delta x0. And it's got to be linear in x3 of x, delta x0. Whoops. And then it's got to be linear in x1 at x of delta, or x0 of x of delta x1, and x1 of x of delta of x1, etc., 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 all the way, of course, to x3 of x delta x3. So it's got to be linear in every single one of those terms. And also, it's got to carry an upper space-time index. So I need to draw a symbol out here, and that symbol is usually given by gamma, and I need to draw the symbol with, it ends up with an upper index, an upper space-time index, and it sums over these other two indices. So it looks like that. So why don't I straighten it out? Gamma alpha d c x d x delta x c. And actually, for convention's sake, and we'll see why, it's defined with a minus sign. And this is how I define this mysterious difference that establishes parallelism. And all I've really done is I haven't made too much progress. I've made a little progress because I've decided that logically, whatever this thing is, it's got to be linear in these two terms. And the only way to do that with all of the different possibilities is to create this Einstein sum off this symbol. And ultimately, it's got to land with an upper index, so this symbol has to have 3 indices, right? Now notice it has 3 indices, but it doesn't necessarily have to be a tensor, right? In fact, it almost certainly will not be a tensor. There's reasons to see that it's not a tensor. It's just an object that sums with an Einstein. It's a bunch of coefficients, right? And inside these coefficients are these magic things that take the original vector and the displacement, takes the original vector and the displacement, and it produces, over here, it produces another vector, right, which is ultimately going to have components of x alpha x plus delta little x alpha, which we'll now write as x alpha of x minus gamma alpha b c x alpha of x delta xc, like that. And that will end up being the parallel vector, right? That is now our parallel vector. And the only thing we've improved upon is we've established that this difference has this linearity in it. So we're left with these guys. And also notice that this is a function of space-time, of course, because it's the field, right? And it's the field value here, but it's the component of the field here, and it's giving me the components of the field here when I correct this with this term, right? When I make this is the sort of the correction, then I get the parallel field and I get its components. I get the components of the so-called parallel field at Q. The point being that I could do this at any different point in space-time, right? Q could be anywhere. Therefore, these components might be different at every different place, and in fact they certainly will, these numbers. So to really think about this correctly, I now need to write it this way. I need to write it delta x alpha equals this number gamma, and it's a function of space-time also. It's a function of space-time as well. And x dx delta xc. And notice that we take the value of this function at the same place, p. P is sort of our anchor, right? That's where the vector that we're interested in lives. We're trying to seek the corresponding vector here. So whatever this correction is, we're going to attach it as a function of space-time associated with the same point p. But this function of space-time, this is actually not a function of space-time. This is 4 times 4 times 4, right, functions of space-time. So there's a lot of functions there. And all of those functions, we need them. We need those functions in order to figure out what parallel is. So now we've reduced the entire problem of parallelism. We've crushed it into these guys right here. And this guy here is the connection. It's also often called an affine connection because there's different kinds of connections we'll see as time goes on. But it is a connection, and it is not a tensor, right? Not a tensor. And what that means is that if we wrote gamma alpha d c e alpha tensor product ed tensor product ec, that makes no sense. It's not a tensor. It's not a tensor, so that makes no sense. It is just a collection of functions. But the subscripting and superscripting always obeys the Einstein summation convention. And you can see why, because I need to add linear corrections in every one of these possible terms. So the affine connection, it's not a tensor, and everything we know about parallelism is wrapped up in the affine connection. And now kind of comes the big reveal, right? The big moment, right? We need this affine connection to make a sense of parallelism. Well, where do we get that from? So the answer is that ultimately, physics will give us this connection, one way or another. Physics gives us the metric, and the metric will give us the connection. That's ultimately where we're going with all of this. But right now, in a mathematical sense, these numbers are arbitrary. The connection is arbitrary. And what I mean by that is we can pick it. It's got to be kind of smooth, right? We're talking about smooth functions, differentiable smooth functions. It's a function of space-time, so it needs to be differentiable in terms of all of the coordinates. You know, it has to be differentiable by the coordinates because it's a function of the coordinates. But these functions, these 4 times 4 functions. Did I say 4 times 4 times 4? It's just 4 times 4 functions. No. There's 4 times 4 times 4. What am I saying? Yeah. So, but they're arbitrary. We have to pick those guys. And once we pick those guys, once we pick what those functions are, we endow the space-time with those functions. So we have this big space-time manifold, right? And that manifold, it comes, or we've got to give it, or we have to find on that thing a connection. And in a moment, I'll write the connection for now as alpha, beta, gamma, like that. But later, we're going to use this symbol for the connection, this upside-down triangle, when we do a second derivation of all this. So that connection is the thing, but understand we give the manifold the connection. And once we assign the connection to the manifold, so we really haven't solved the problem of parallelism. The fact is these vector spaces are just too separate. There's no mathematical way of taking any vector field, you know, if we define some vector field, we can never take that vector field and just assume or find a natural connection, some sort of natural manifold that belongs with that vector field. If we build a manifold, there's no way to assume some sort of natural connection on that manifold that just goes with the manifold, that once we know the manifold, we know the connection. That's not how this works. It works totally differently. This connection is something that has to be endowed to the manifold. And once it's endowed to the manifold, then we can talk about parallelism. And once we talk about parallelism, we can use this definition here to define the covariant derivative. And in fact, why don't we flush that out, right? So let's take that covariant derivative now and come up with the actual notation we're going to use for this object, right? I'm going to take this and we're going to finish it up. That covariant derivative is, well, that first term was delta c. So first of all, I'm going to write the covariant derivative like this. I'm going to give it an upside down delta with the subscript c. That's the covariant derivative of the vector field alpha a. And that c is meant to be an index, right? It doesn't mean covariant. It's just an index, a 4-component index. And that's going to equal the partial derivative of the field with respect to the coordinates. And it's going to be, we know that it was originally minus this thing. There was a c there, right? There was a c here, right? Because it's with, it comes from this delta c here, so there's a c down there. So we make the substitution here, and that substitution is minus gamma alpha bc of x alpha delta xc, right? And the delta xc here will cancel with the delta xc there. The minus sign here will cancel with the minus sign there, and you'll end up with plus gamma alpha b c x. Oh, this is an xb, right? And this is the definition of the covariant derivative. And you can see why we chose the negative sign in this definition here. We chose the negative sign when we defined this mysterious piece that identified the parallel components. We chose that negative sign so that when we actually defined our covariant derivative, we would end up with a nice little positive sign. Not that it really helps, because we can take covariant derivatives of forms in which the negative sign pops back in, but this seems to be the standard. So if I have a vector field, I write down the components, and I can say the covariant derivative of that vector field is going to be the partial derivative of the vector field with respect to the coordinates, plus this term here, which is the connection multiplied by the components of the field. And this will correct this thing to give you a derivative. And notice what this guy is. It's actually, this is a real space, these are real indices here, right? So this has got one index up and one index down. So this thing here is a 1-1 tensor. This definition here, if we want it to survive and make sense, we're taking a derivative, a covariant derivative of a vector field is a 1-1 tensor. So a vector field is a 1-0 tensor. This becomes a 1-1 tensor. And actually, these are the components of a 1-1 tensor. So the real 1-1 tensor is going to be delta c x alpha, and then it's going to be in another way that we would write this. There's a couple ways of writing it, but probably the most common way that you'll see it is with a semicolon and a c, like that. That means the same thing. And my favorite way that I do it in some of the work that I'm trying to write, I use 2 bars. I don't like the grammar of the semicolon, but that is very, very standard. This is the one you'll see the most in the best books. You see this in the more elementary books, but you see this a lot everywhere. This is probably the most common. This one is less common, but is cleanest to me. And that symbol, and with that symbol, we could actually make perfect sense, and we would write del alpha cross dxc, like that, right? Which is the basis of, that's the coordinate basis, right? So this is a 1-1 tensor. So ultimately it must look like this. The way these are written, it's just the components. So everything here, all of this is implied, and I've kind of gone on and on about that in other lectures, about how typically they just work with components and they leave this off. But if you want to emphasize the fact that this is a 1-1 tensor, go ahead and throw in your basis vectors. That's okay. That's perfectly fine. And the coordinate basis, this is what they are. And then the last thing we need to know before moving on to a different derivation of this is that for a scalar field, for a regular field, say psi on spacetime, which is a real valued field on spacetime, the covariant derivative of that thing, which could also be written as psi of x alpha like that, that's simply defined to be the partial derivative with respect to alpha of the coordinates of psi of the coordinates, right? This, if you're just a scalar function, if you're not a vector or a covector or a tensor, then there is no, the connection does not matter when the derivative is taken. So that's sort of the rule for the 0, 0 tensor, right? The function on spacetime. So that's the most elementary derivation. It really, it all goes back and it leans on this notion of how do we understand parallelism, and parallelism becomes our baseline by which to measure the differences in vectors, and we come up with this notion of covariant derivative. But all this concept of parallelism gets jammed into these functions, these 24 functions, and they define the connection on the manifold. And that's something that we have to supply. So we never really answered the question, oh, how do we figure out what the parallel vector is up here? How do we figure that out? And the answer is, in the pure mathematical world, we don't. We assert what parallelism is, and then we measure all derivatives relative to that. But in the world of physics, we let the physics tell us what that parallelism is. And a great deal of our work, as we get into general relativity, is going to be exactly that, trying to figure out how the physics tells us what these numbers are. Okay, so the second derivation of this is long enough, and this has gone on long enough, that I'm not going to do it here. I'm going to do it in the next lecture. We're not completely finished. There's a few other points to notice. One is, first of all, that these covariant derivatives, by the way, increase the tensorial nature of things. So where was that description? Hold on, let me find it. When we come down here and we look at this, we started with a vector and we took the covariant derivative, and what do we end up with? Well, we end up with something with two indices, and it's a tensor now. So the covariant derivative increases the rank of these objects. And that's important. It's also true for the scalar field, right? The tensor, the scalar field becomes, instead of a 0, 0 rank tensor, it becomes a 0, 1 rank tensor. So that's an important thing to notice. The next derivation we do is going to be far more abstract. You'll notice that everything we did here was dependent on the coordinates, right? This whole notion was the field as a function of the coordinate. The field is a function of the coordinates. Everything here is coordinates, coordinates, coordinates. The more abstract version of this is the coordinate-free analysis, and that's what we're going to do next time. And I think the coordinate-free analysis is important because the more modern treatments of relativity live strongly in the coordinate-free world. Everything here depends on this being a manifold, and as a manifold, that means it's always a manifold. Even in the coordinate-free world, in principle, you're dealing with something that's a manifold. But when you actually are using the coordinates in this derivation. Everywhere is a coordinate. Coordinates, coordinates. Everything, there's derivatives involve coordinates, and the final expression has the coordinate bases in it. So we can get away from that. We can do this derivation in much greater generality without the coordinates, entirely on the coordinate-free manifold. And it's really worth doing, and it's really worth getting to know, and we'll do that in our next lecture. And then we'll go back and look more closely at these, and we'll realize some important facts, namely that it's symmetric in B and C, in these lower indices. The symmetry in these lower indices is very important because it means the spacetimes in general relativity are what we call torsion-free. Mathematically, you can have torsion, but in our science, we discovered that general relativity has torsionless connections. And because of that, it's greatly simplified. And there are alternative theories of gravity where the connection is not symmetric in BC. And those theories are not what we're going to be talking about. So I'll see you next time, and we'll cover the covariant derivative all over again.